Good afternoon. Yeah, I'm Jeff Cooper and my colleague Kumar Ramaswamy. It's great to see people again. It's after 3 years. Real great to be back. Today we're going to talk a little bit about ATSC 3. We'll give a little overview, just brief introduction of some parts of the standard and its flexibility. And we'll also talk about our product we call iLux. iLux is both an ATSC 1 encoder solution and also supports ATSC 3. And we're proud that over the last several years we have over 350 stations on air with our iLux product for both ATSC 1 and 3, and ATSC 3 certainly growing. That includes a New York City station, which we're proud to say is one of the first in the New York City area just this year for ATSC 3. So ATSC 3, just as again a little introduction, many people know a lot about it already. It's a new broadcast standard in the US. It's a very flexible, feature-rich standard built on IP technology, which is really unique for a one-way transmission broadcast standard. It offers a slew of capabilities. You can certainly stand up video channels like a traditional broadcast station, but it also offers the ability to break your spectrum up almost dynamically on the fly to provide data services and other unique services that really has not been done on broadcast before, and we'll get into that, especially with Kumar's discussion. But first, just to give an overview of the video features of ATSC 3 and our iLux product. Our iLux product is actually a software platform. It's a Linux-based server that we've been developing for years and keep adding features to it. And it goes hand in hand really well with ATSC 3 since it's also a very flexible standard, and there are a lot of new capabilities people are bringing to the market, over time. So we're proud that we can put this product in TV stations today. They can get their ATSC 3 signals on the air, typically starting with some video channels, and then with software updates we can enable them to add new features and new capabilities, especially in the data side of the world. So a very simple broadcast chain. You have an encoder. In our case, our iLux encoder supports up to 2 4K channels, 8 HD channels, or 25 SD channels, or any mixture of those. So you could really fill, a 6 megahertz band with a full bouquet of channel lineup if you want to. But what we're really seeing in the industry is people are putting up, less than that, fewer channels, and keeping some of their bandwidth available for new services like data. So this is just a diagram of a very simple broadcast system. You have the encoder. In our case, we can take a variety of input signals, everything from analog to digital uncompressed, compressed signals off the internet, convert it to the ATSC 3 formats of HEVC. Today there's a little bit of AAC, and also the AC4 codec is coming, which is part of the standard for higher compression for audio. That goes through a signaling and delivery service where other parts of the data stream get mixed in. The program guide, advanced, this is where the data services can get inserted, things like that. And then all that is modulated and sent to the transmitter. In our deployments, we've seen 2 different types of architecture, so we thought that would be interesting to go over. One we call centralized, where again the encoder and the signaling service and the gateway are all in one central location, and you may have multiple transmitters. One may be just in the near vicinity and it's just on a private network, or you may have something that goes over the internet, but there's just one central studio with the encoding and gateway. But we've also run into cases where people have multiple transmitter sites in different geographies, and they want a common studio encoding all the bouquet of channels, but they only maybe want part of those channels on one transmitter and part of those channels on another transmitter. Some of that may be overlapped, so there's some efficiency gains by keeping it all in one central studio. So we've been having some deployments like this where you separate the encoder and you separate the gateway and the signaling server at the transmitter sites. So you end up with one encoder and two gateways. So again, kind of going over some of the features of a signaling server. There's a standard called A331 in ATSC, which is a very full-featured standard, which we support. You can support up to 25 live or non-real-time streams over ATSC3. All this is encoded and then sent over an IP type protocol with the route protocol. The video is a dash formatted over-the-top signal. It looks like something you'd find on an IPTV network. Again, the video coding is ATBC and audio is AAC and AC4. A couple other nuances we've seen in the actual deployments. So EAS, the emergency alert system, still you have to support, the ATSC1 type emergency alert system. So in other words, you need to be able to get your, when an emergency alert comes, and that tone that you hear on your TV with the weather warning or whatever it may be, that is still the old way. There are some new advanced features that are part of the ATSC3 standard you can do called AEA, which can go through the gateway and it can enhance some of the information. But when the government sends out, tornado warning, the encoder has to get that on the screen. So that's still a very local input we have to support in the encoders. Program guide is similar. There is new, more advanced program guide features coming, and there's still a lot of work going on in the industry. So the legacy program guides are still there, and as we see more and more deployments, there are the more advanced guides with the new ATSC3 formats coming along. We still do station ID in the old way. We make sure the call letters get on the screen every hour. We still have some ability to do old-fashioned text scrolling and things when customer needs it. So we're still kind of in this, rolling out phase, I think, is a good summary. So now we're going to get into what the data services are. As I mentioned, ATSC3 is very flexible in that it can both do video and data type services, and we're starting to see more and more interest in data from our customers. So again, kind of the trend we're seeing is stations are putting up their video channels, and now they're starting to add the data services. So my colleague Kumar is going to come up here and talk more about that.
Thank you, Jeff. That was a pretty good summary of what we are doing in ATSC3. We start out with basic video services. Most operators, most station owners, what we see them do is start out with offering a bouquet of video channels, but then they have spare capacity. As a revenue generator, they are starting to look at all data services of all kinds. And the interesting thing about the ATSC3 standard is that it has got, it really looks like an IP pipe, one-way IP pipe that will allow you to start sending down data services of various types. So why should we start doing ATSC3 for data services? The starting point, in fact, in the previous panel we talked about this as well. Cellular systems, right, have been designed for both 4G and 5G or any of these systems. They are actually designed to be point-to-point systems. The idea is they are very, very useful for personalized data. When you're trying to, when an end consumer tries to consume personalized data, Cellular systems are designed for that, and they are very highly efficient to deliver that. But when you start to talk about common services such as a broadcast live game or a software download into an automobile like a car, or a software uploads for all these autonomous cars, I don't think it's a very efficient for cellular systems to be delivering them, because as you scale the number of users, cellular systems have to do a point-to-point with each user. So they use up a lot of the spectrum to do that. So here is where I think broadcast systems overlays of broadcast overlays, especially in the United States, where the DMAs have been designed very, very efficiently to do broadcast delivery. This has been designed over a 50-year period, starting with analog television. And I think they do an excellent job of covering DMAs, population centers, mass distribution of content has been done very efficiently with broadcast. And ATSC3 will, using the same transmitter infrastructure, they can deliver much higher bandwidth, much more efficiently than is done with cellular systems. So the short story here is ATSC3 has got a big role to play to deliver content, certain types of content, live programming, live video programming, and data content that is common to all users, not personalized data, but data that is common. Like, for example, if you're trying to do software update on all the Ford's cars in the country, or all the Teslas in the country, you're much better off using a broadcast medium to do that than cellular. It's just the use case, right? And that's why I think ATSC3 is an ideal broadcast pipe to do that. It is very cost effective, and we can look at some specific examples. And it is extremely cost effective compared to cellular ways of delivering this kind of content. So the next point I want to kind of bring up is, in order for ATSC3 to support the system, what kind of an ecosystem do we need? So the first step is, once the content owner says, I want to distribute this day, let's say a software download, a 2 gigabyte software download to all the vehicles in the country. Let's say they want to make that statement. What do they have to do? What is the ATSC3 ecosystem that we need to put in place in order to do that? The very first step is they need to be able to go to a cloud website or a cloud portal and reserve capacity, right, in the entire infrastructure. So, for example, if a Tesla car company decides that I want to update all my Chicago DMA or Las Vegas DMA vehicles, so then they need to be able to specifically reserve bandwidth in order to be able to do that. So they need to have, and that needs to be done. This is an NRT service, because this is not being done not in real time, but this is just a download service. So they need to schedule this service. So they schedule a certain amount of bandwidth, and then they need to reserve that bandwidth. And similarly, the Chicago DMA station now is offering, if you recall what Jeff was talking about, they are offering video services, but then they have a certain amount of spare capacity available for data services. Now, the spare capacity that the Chicago DMA station wants to offer, it needs to offer that capacity into the infrastructure. And so this kind of a cloud, the box is shown in blue, there is a set of components that need to exist being offered by some providers that do this bandwidth arbitrage. Providers on the station owners on one hand offering a certain amount of capacity, and data distributors who want to distribute this content into the infrastructure. This kind of mating has to be done in a marketplace on the internet. And that is what that whole capacity, the cloud marketplace needs to provide. A second component that needs to come into existence is at the station level. At the station level, you need to have a notion of a scheduler. So, for example, if I'm a station owner and I'm offering both video and data services, and I have offered to about 20% of my, or 10 or 20% of my capacity for data services, I still need to schedule it. So software component needs to sit at the station level that is offering the scheduling of these services. And so the content gets downloaded to the station, and then it gets scheduled out to be multicast over a carousel or over a broadcast medium over several times during the day to be sent to the end devices. a third component needs to exist to reliably receive this software downloads or this kind of data service downloads at the end device level. Because this is a one-way medium, it's not an IP service where, if you don't receive something reliably, you go back and request a rebroadcast. That cannot happen here because it's a unicast mode of transmission. So you need to still have some software in the receiver to reliably piece together, multiple shots of the content that was received to finally receive it in a very reliable manner. And this software needs to sit on all these end component devices as well. So there are three total components that need to come into play. The cloud providers that need to do the marketplace to allow to match up content owners to the end receivers. Then at the station level, you need these kind of scheduling mechanisms. And then finally, in the receiver, you need software that will reliably receive all the content. There are several trials that we have heard about that are being done already today. Sinclair or Arc Media have talked about end-to-end services that they have started to deliver. So they are bringing together some of these components, but all of these components need to exist with all broadcasters and all station owners so that you can all start offering these end-to-end services as an overlay. So what needs to happen at the station level for data services is that you need to now allocate physical channels to allow for these services to go reliably over an over-the-air channel. Similarly, you need to allow for data carousels. These things are not, since you're not offering these, it's a wireless medium and different receivers are going to have different receive capabilities. You need to allow for data carouseling. Send these pieces of content many times during the day or many times during the course of the day so that the receiver can actually receive it, piece it together and actually have the data available completely in a lossless manner. So you need to have other mechanisms such as error concealment and resiliency, and a lot of this can be even outside the realm of the standard. These are pieces of software that need to exist both at the head end and at the client side in order to reliably deliver this content over the system. And in our company, we are in the iLux, we are also further optimizing this to allow for video services and data services to be, very efficiently use the broadband, to use the available ATSC3 spectrum so that you can deliver both these services in a pretty reliable way and also in a very efficient way. So I just wanted to spend a couple of minutes to talk about the economics of ATSC3 data delivery. There are two examples. One example, a station owner agrees to allocate about 20% of the spectrum for the data service. So usually you use a very robust modulation, QPSK, low data rate code. You get about a half a megabit of throughput. And the threshold of operation, if you notice, is a very, very low, negative 1.3 dB. This means you get a large radius of operation, a large DMA, and then the carousel repeat factor for this would be about 5 to very reliably deliver this data content into the end clients. A second example, you get about the spectrum allocated is about 25% for the data service from a station owner, 64 QAM modulation, a higher code rate. You get a much higher throughput. You get about 6 megabits per second of throughput. So the reason I bring these numbers up is you start to compare these numbers against what kind of throughput you get with ATSC, with 5G and 4G and 5G. You start to approach those kinds of bit rates. And the carousel repeat factor in this case is 10. So the key point, the way to compare ATSC3 datacasting versus cellular is the cost per gigabyte of transacted for data transfer. In the 4G or 5G, this ranges anywhere from, they predict it will get to about 20 cents a gigabyte. Today it is well above $2 or in the $2 or $2.50 range per gigabyte of transfer. And the number of endpoints in a DMA, to remind everybody, could be anywhere from 1,000 users to 1 million users inside a single DMA. So what we will see is that ATSC3 will tend to become extremely efficient if you're delivering to a lot of users at the end, to a lot of endpoints within a DMA. Graphically, the cost per transmitted gigabyte In ATSC3, because it's a broadcast mechanism, it's going to be flat, right? It's independent of the number of receivers. But in the 4 or 5G, the cost per gigabyte increases as the number of receivers go up. So there is a crossover point, definitely, when you start using ATSC3 to deliver these kinds of services. In summary, what we want to talk about is, ATSC3 can deliver very comprehensive video services, fully branded, multiple SD, HD or 4K streams with guide, emergency alert and a lot of other features. Pretty much looks like a wireless cable or a cable service. There is potential to use part of the spectrum for data services in ATSC3. And it can compete very effectively, and a lot of our economic models show that, with 5G for certain types of broadcast applications. So station owners can start with video services, and as the ecosystem matures, the economics will support the delivery of data services over ATSC3. Thank you very much. I'll take any questions if there are any. Yes. Yes. So the question is, are there the components, bringing the components together for the end-to-end software delivery of services, data services over ATSC3? Yes. So our company is particularly igolgi. We are involved. We started out by making ATSC3 station equipment, namely the encoder, the signaling gateway, and the broadcast gateway. What we are doing right now is overlaying software services on top of that. So we are going to be, at the end of summer, we are going to be offering APIs for customers, both on the cloud side as well as the station, at the level of the station. What we are not doing yet is the receivers, because one of the things we are looking for is partners on the receiver side, because we don't build receivers. So we are looking for partners on the receivers so that we do have software available for receivers that can do more reliable reception of this kind of data services. So we are actually talking to a few partners at NAB this year on the receiver side. But to answer your question, at the end of summer, we plan to launch both at the level of the station and at the level of the cloud software services to allow for APIs. We'll be offering open APIs for people to integrate against.